Good morning. Today we want to present about diode as clipper and clamper. My name is Hema, and I have another two more groupmate, one Azrina and Kojowi. We are from PARC 21. Okay, the introduction is a semiconductor device known as a diode only permits current to flow in one direction. Diodes are frequently employed in signal modification circuits called clippers and clampers. Because of their rectifying ability in analog and digital electronic, these circuits are essential for modifying signal baselines, limiting voltage, and shaping waveforms. So for diodes as a clipper, without changing the rest of the input signal, a clipper circuit eliminates clips to keep signal from going over a predetermined voltage level. It makes use of diodes either with or without bias voltage. So there are four clipper: positive clipper, negative clipper, bias clipper, series and parallel clippers. So first is positive. For positive clips the positive half cycle of the input signal. For the negative clips the negative half cycle. For bias, use a DC voltage source along with the diode to clip the signal at a desired voltage level rather than at zero voltage. Series and parallel clippers, depending on whether the diode is connected in series or parallel with the load. So this principle, when the input voltage over a specific threshold, the diode become forward or backward bias, blocking or rerouting that portion of the signals. The signal can through when it is reverse bias because it's function as an open circuit. Okay, so this is a example of bias clipper circuit. So this is the diagram that look like. So these are the parallel biased clipper. So there are simple parallel clippers and biased parallel clippers. So these are the diagram. If the simple, it will go down or up. If biased, it will go in variety shapes like that. Okay, for this one, for series clippers, there are positive and negative and bias series clippers. Okay, so there are the image for positive and negative and the bias series clippers. Okay, so this is for diodes as a clamper. Without altering the waveform shape, a clamper circuit moves the entire signal waveform vertically up or down. Through the use of diode, capacitor, and occasional a resistor, it clamps the signal to a different DC level. So for this, there are three: positive clamper, negative clamper, bias clamper. For positive clamper, it shifts the signal upward so that all part of the waveform become positive. For the negative clamper, shift the signals downward so that all parts become negative. And for the bias clamper, used an additional DC voltage to set the clamping level. So the working principle for clamper: the capacitor charged during a particular waveform cycle when the input signal is applied. The entire waveform shifts are a result of the stored recharge adding or subtracting from the input signal voltage. So these are the diagram for biased clamp. So these are the diagram, so you can see the diagram. So these are for clamp circuits. So these are the diagram that the clamp circuit will look like. Okay, these are the application for clippers and clampers. Clippers protecting circuit from voltage spike and clampers signal restoration in communication. For clippers, analog signal to digital lock. For clampers, DC distortion in communication, and clippers is wave shaping, and clampers are modifying DC level of signals. So the conclusion is in circuits that shape wave, such as clippers and clamper, diodes are essential components where clampers modify the DC level of signals. Clippers are used to limit voltage level. Both have several uses in communication, protection, circuits, and waveform modification, and are crucial to electronic signal processing.
And now for the part B, we have NPN-BGT2N3904 transistor. This transistor is widely accessible in multisim, which facilitates analysis and simulation. It frequently utilized in real-world circuits and electronics education for simple switching and amplifier applications. This general-purpose low-power NPN transistor is appropriate for circuit analysis at the beginning to intermediate levels. Because of the datasheet through documentation, precise manual computations and verification are possible. For N-channel FET, we have the N7000 MOSFET transistor. Multi-sim standard component libraries make this transistor is easy to locate. It is well like a small signal N-channel MOSFET, perfect for a low power load switching. This mode of enchantment MOSFET, which is helpful in demonstrating how drain current is controlled by gate voltage. It operates differently from BJTs, which BJT is required to pace current, and due to its low current demand. Because of thoroughness, the datasheet can be used to compare manual and simulation calculation. It is also helps to clearly show how voltage controlled FET and current controlled BJT control mechanism vary from one another. This is the characteristic graph transistor for BJT2N3904, and this is for FET2N7000. This section's goal is to use a voltage divider biasing arrangement to examine and contrast how a bipolar junction transistor (BJT) and a field effect transistor (FET) operate. In transistor circuit, biasing is necessary to establish the proper operating point (Q point) for linear amplification. The chosen transistor, which is the 2N7000 for N-channel MOSFET and the 2N3904 for NPN-BGT, are both often used in electronics for switching and amplification. Every type of transistor is used in the design and construction of the voltage divider by circuit. VB, VE, VRC, VC, VGS, ID, and VDS are among the pertinent voltages and currents that are manually calculated and subsequently validated through simulation using multisim. The operational distinction between voltage-controlled FET and current-controlled BGT devices are clarified by this analysis, which also shows how it reacts to the identical biasing technique. And now for the methodology, we have design, calculation, and simulation. This is the circuit for NPN-BGT to N3909. The two resistors R1 and R7 form a voltage divider that provides a fixed voltage to the base of the transistor. This base voltage allows a small current to flow into the base, which turns the transistor partially on. This is the circuit for N-channel FET to N7000. The gate of the MOSFET is connected between R1 and R7, and the voltage divider R1 and R7 sets the gate voltage to turn the MOSFET on. The source resistor R8 provides negative feedback, stabilizing the bias point.
I'm Joey and I'm going to explain the rest slides. This slide is about calculation of BJT and FET, and here are the working steps. Here are the results of simulation of circuit we did in Multism. After that, for BGT2N3904, we did a compare of results between the calculation and simulation. And the results we compare are VB, VE, IE, VRC, and VC. And for JFET2N7000, we also do comparison between results of calculation and simulation, which are BGS, ID, and VDS. So the third one is collector
So through this
voltage.
table,
got
we can
calculation
see
is
clearly the comparison
8.03
between the
voltage, but the
calculation and
simulation is
simulation,
1.42
and also the
voltage.
discrepancy and possible reason.
So first,
The
for
large
the base
discrepancy
voltage, the
maybe is
calculation
based
we got
on the
is
incorrect load
2.05
resistor
voltage, but the
value
simulation is
or transistor
11.46
saturation.
voltage.
The
And then the next one
discrepancy
is
is very
emitter
large.
current.
The
We
possible
got
reason is
calculation is
maybe the incorrect biasing
1.985
resistors or
mA, but
simulation
the
setup
simulation
error.
is
And then the next one is emitter voltage.
52 mA. We got the
And then this
calculation
large
1.35
large
voltage, but the simulation
discrepancy
is 10.55 voltage. So the
large discrepancy is
discrepancies
large
possible
also.
reason is miscalculation
And
of IE
maybe
equals to
because of
VE. RE
VBE or
assumption
incorrect RE value.
0.7 voltage may not match the actual transistor
So
model.
the third one is collector.
And then
And
for
also
gate
drain
source
source
voltage, we
we
got
got negative
3.95 voltage for
2.04
calculation
voltage for
and
calculation and
8.11.83
9 voltage
M
for
voltage for
simulation.
simulation.
The
The
discrepancy
is very
will
large, and the possible
because
reason
of
is
the
incorrect
incorrect
biasing or
assumption of
simulation
VGS
model
or
mismatch.
channel length modulation
And then the drain
effects.
current, we got
And also drain
4.235
source
mA
voltage,
for
we got
calculation and
3.95 voltage for
4.47 mA
calculation
simulation.
and
This
8.9
discrepancy is minor.
voltage for
The
simulation.
possible reason
The
is
large
close match,
discrepancy
slight variation due
will
to component
because
tolerances.
of the incorrect.
This table is comparing the differences between BJT and JFET. So the control mechanism of BJT is current control, which is base current, and the JFET is using voltage control. And then the next one, input impedance. BJT is low and JFET is very high. And next is power consumption. BJT is higher due to base current and JFET is lower. Negligible gate current. And then the last one is switching speed. BJT is moderate, but JFET is faster due to no mandatory carrier storage. Discussion. After the experiment, we can prove that both transistors successfully demonstrated their fundamental operating principles. BJT exhibited current control amplification. JFET showed voltage control characteristics. Measured parameters generally follow expected trends for each device type. Minor variations between calculated and simulated values fell within acceptable margins for educational purposes. And then the next one is the practical observations. The BGT required more precise biasing but delivered higher gain.
The JFET offers simpler voltage control with excellent input impedance, and both devices maintain stable operation within their specified range. Simulation results effectively complemented theoretical predictions. And also implementation insights. Voltage divider biasing work effectively for both transistor types. Each device shows its characteristic advantages. BJT for current application and JFET for high impedance applications. Component tolerances and measurement technique accounted for most variations. Conclusion. The experiment successfully demonstrated fundamental differences between current control BJT and voltage control JFET devices, practical implementation considerations for each transistor type, the complementary nature of these devices in electronic design, and then the educational value. We reinforced important concepts in transistor biasing techniques, parameter measurement methods, simulation vs theoretical analysis, and then provided hands-on experience with two essential semiconductor devices. And then the next one is the design recommendations. VJT remain preferable for high gain amplifier stages and current driven applications, but the JFET excel in high impedance input stages or voltage control circuits. And then we need to always consider the proper biasing networks and device operating limits simulation verification. The presentation will stop at here. Thank you.